Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are going to talk about hidden Markov model. Of course, I didn't invent any of today's material. I took a lot of today's content from the textbook written by Christopher Bishop, in particular chapter 13. I also took some of the materials from chapter 17 from the textbook written by Kevin Murphy, as well as chapter 12 in the unpublished textbook written by Michael Jordan, which can be accessed from this link over here, and chapter 11 from Simon Prince's textbook on computer vision. I strongly encourage every one of you to read, especially the first reference material from Christopher Bishop chapter 13 after today's lecture. Hopefully, by the end of today's lecture, you should be able to describe the joint distribution of a hidden Markov model with what we call the transition and emission probabilities. And then we'll look at how to use the EM algorithm to do maximal likelihood estimation of the latent variable and unknown parameters in the H&M. Next, we will look at how to use the forward-backward algorithm to evaluate the EM algorithm. And finally, we'll apply the VTP algorithm to find the maximal probability and its configuration on the hidden Markov model. Recall that in the last week's lecture, we mentioned that we are interested in finding the maximal likelihood of this joint probability distribution of X, Z, as well as theta, where this joint probability distribution consists a set of latent random variables, which is unobserved random variables, as well as the unknown parameters. And of course, we are also given a set of observations. These are the observed random variables. And the task was to find the maximal likelihood of the unknown parameters, marginalize away the assignment or the latent random variables in this joint distribution. And we saw that the EM algorithm, the expectation maximization algorithm, can allow us to find the latent random variables as well as the unknown parameters in an alternating fashion. Today we are going to continue to look at this joint distribution of Px, Z, and theta. But there is subtle but important difference here. In last week's lecture, we saw that this particular joint probability distribution is modeled by a graphical model as shown over here, where this observed random variable is xn and this latent random variable is zn. So we are assuming that all the latent random variables are independent from each other. This means that if I observe Z1 and Z2, they are not going to affect each other. And intuitively, what we can see here is that suppose that we are given a 2D feature. If you recall in last week's lecture, suppose that each one of these data over here, each one of these cross over here represents a feature from the MNIST data set. For example, this is 1 and this is 2, for example. So this is 1, 2, and 3, for example. And we note that we can visualize, suppose that we can represent each one of these MNIST data, each one of these handwritten digit with a 2D feature, and we can plot it out in the 2D plots that look something like this. The different clusters of digits will form the clusters respectively, and this is what we will get here. If suppose that in this particular data set we only have 3 numbers, 1, 2, and 3, and what happened here is that every one of these random variable or every one of this observation here, it's associated to an assignment into the cluster, either 1, 2, or 3, which we write z equals to 1 or z equals to 2 or z equals to 3, for example. And we say that each one of these latent random variable or this cluster, they are actually independent of each other. This means that if I were to draw a sample of this guy over here for my observation, and the next sample that I drew from the distribution, it's going to be independent of the first draw of the sample. over here, which belongs to class 1. So I might end up drawing a second sample from any of the cluster over here. So they are completely independent. Hence, this plated notation in my graphical model over here. So this plated notation means that I repeat this z pointing to n number of times, such that they are all independent of each other, where all the clusters or all the assignments, they are independent of each other. And in today's lecture, although we are going to look at the same probability distribution, the same joint probability distribution of x, z, conditioned upon theta, where x is still an observed set of random variable, z is still a latent set of random variable, and theta is still our unknown parameters. The difference here is that we are going to remove the assumption that all the latent random variables are independent of each other. We are going to say that the latent random variable at this time step of Zn, it's going to be dependent on the previous random variable of Zn minus 1. And we'll see that we'll write this dependency of Zn and Zn minus 1 as the conditional probability of Zn conditional upon Zn minus 1. And intuitively, what this means is that suppose that we are given some observations, the 3 clusters as the example that we have seen earlier. But now we are going to say that the random variable or the observed random variable that is drawn from the distribution at this time step of n, it's going to be dependent on the previous observed random variable. Suppose that the previous observed random variable is drawn to be this sample over here, and it's taking a class of z equals to 2, and this is Zn minus 1, where it's in the previous time step, it's equals to 2. This means that I'm drawing the observed sample is drawn from cluster 2 over here. And we're going to say that the next sample that we are going to draw, which is xn, is going to be dependent on the class of xn minus 1, which is Zn minus 1 equals to 2. So this means that there is a certain transition probability. There is a certain probability that takes me from this particular latent random variable in the previous time step to the current time step. And it can be represented by this transition probability arrow over here. So we'll see that this is going to be a probability value where we transit from the previous state to the current state of the observation. So there is a certain probability that I'm going to draw a sample here, or there is also going to have a certain probability distribution that I'm going to draw a sample here, given that I have already drawn a sample in this class number 2 over here. So we are going to follow this probability distribution, or there could also be a probability that I'm going to draw the same a sample from the same cluster following this particular arrow over here. So obviously we'll also see that all this, the probability value, which we call the transition probability value, condition upon that the previous time step of the observation belongs to class 2, it's going to sum to 1. This means that the transition probability, given that Zn minus 1 equals to 2, it's going to sum to 1. Having seen this example, we can say that HNM, or hidden Markov model, is actually a natural generalization of the mixture model, which can be viewed as a dynamic mixture model. Again, let's compare the two graphical model. The mixture model, graphical model, it looks something like this, where Zn is pointing towards xn, which is our latent random variable pointing towards our observed random variable. And this set of latent random variable, they are all going to be independent of each other, hence this plated notation over here. Of course, there's also a reliance on our pi, which is our mixing coefficient, as well as the sigma and mu, which is our mean and covariance of the normal distribution in the Gaussian mixture model. So, but in general, this need not be a Gaussian mixture model, so it could be a mixture model. And we can see that a HNM is going to be a natural generalization, where each one of the random variable, latent random variable at this current time step is dependent on the previous time step. Hence, this will give rise to a hidden Markov graphical model, which looks something like this, where this could go up to all the way to Zn, and this is Z1, Z2, and all the way to Zn, and the observed random variables are here, where this could be x2 all the way to xn over here. So we can see that the fundamental component of this hidden Markov model is actually the same as our mixture model over here, where it consists of z pointing towards the random variable, the observed random variable of x, which appears on both of this graphical model over here. The only difference between these two graphical models is that in the hidden Markov model, we get all the random variables of latent random variables at the current time steps. They are going to be dependent on its previous time step respectively. And whereas in the mixture model, all the latent random variables, they are independent of each other. Here we can also say that this linear chain that is formed by our latent random variable, it's also called a Markov chain. And in this case, where the current time step of the random variable, the latent random variable, is dependent on only the previous time step. This means that Zn is only dependent on Zn minus 1. We'll call this our first order Markov chain. So the Markov chain, which resulted from the dependency of the latent random variable, in the case which we have looked at is the first order Markov chain, where the current latent random variable is dependent on only the previous latent random variable, gives rise to a graphical structure which is known as the state space model. And we'll see that this particular state space model can be described as a transition matrix, which describes the probability of transiting from one state to another state between different time steps. And this particular state space model has to satisfy the key conditional independence property of Zn minus 1 and Zn plus 1 are independent given Zn. So this means that we are looking at a linear Markov chain where the latent random variable is given by this Markov chain over here, where this is Zn minus 1 and Zn, and this is Zn plus 1. So we will say that Zn plus 1 is conditionally independent of Zn minus 1, given that we have observed Zn. We can easily see this from the d-separation principle of the head-to-tail structure in this linear chain over here, where Zn minus 1 is decoupled from Zn plus 1, given that we have observed Zn over here. Now, more formally, we can denote the first order Markov chain using this particular graphical model over here, where we can see that there is a linear Markov chain governing the latent random variables, where it fulfills the condition or the conditional independence of Zn minus 1 is conditionally independent of Zn plus 1, given that we have observed Zn, as we have seen in the previous slide. Where we can actually verify this easily, where we can see that if we have observed Zn over here, since this is a head-to-tail structure, Zn minus 1 and Zn plus 1 would become de-separated from each other, because the baseball wouldn't be able to pass through this particular path over here. And for every latent random variable, there will be an associated observed random variable, which we denote as xn in general. So now the joint distribution or the joint probability distribution of this hidden Markov model, or the first order hidden Markov model, is now given by this particular expression over here, where we write the joint probability distribution of all our observed random variable as well as all our latent random variable to be equals to a prior distribution of the first latent random variable multiplied by the product of the transition probabilities. We call this the transition probability because this particular probability distribution here tells us that given that we are at the state of the hidden state at the previous time step, what is the probability that we are moved to another state in the next time step. And we call this guy over here the prior probability distribution, because this is Z1 over here has no parent in the graphical model. And the third term that we are going to look at would be what we call the emission probability distribution, or otherwise the observation or the likelihood probability distribution here, where this is directly a local conditional probability of X, having observed X, conditioned upon the associated latent random variable of Z. So we will write this as Xn conditioned upon Zn, since every latent random variable has its associated observation over here. So we'll look at the definition of each one of these probability term in the next few slides. So one of the interesting thing about this joint distribution in comparison to the mixture model that we have seen in the previous lecture is that there is an additional term of the transition probability, where we can see that this particular transition probability actually describes what we have in this, or what we have addition in this hidden Markov model compared to the Gaussian mixture model or the mixture model in general. So this particular transition probability actually describes the transition of the latent space from one time step to another. So in this lecture, we'll talk in detail about the hidden Markov model, where the latent random variables Z over here, it must be a discrete set of random variable, and the observed random variable can be either discrete or continuous, where these are the X over here. It can be either discrete or continuous, and we'll call this the hidden Markov model. So what is out of scope in this particular lecture, and in fact in this particular course over here, is what we call the linear dynamic system, which we are not going to cover, where the definition of this is that the latent random variable as well as the observed random variable are both continuous. So in this case over here, Z would be continuous, which can be described by the linear Gaussian model. In the case where the latent random variable as well as the observed random variable are both Gaussians. So in this particular case, if you are interested, you might want to look at the particle filter algorithm or the Kalman filter algorithm, which is used to infer the linear dynamics systems. And unfortunately, we do not have enough time to cover this in our course, but I strongly encourage those who are interested to look into these two particular literature, which can be very interesting. So now let's look at some of the example of the hidden Markov model before we go into the mathematics of the how to learn the unknown parameters, as well as to how to infer for the latent random variable. The first example that we're going to look here, it's the speech recognition example. Suppose that we are given a microphone. When you speak into a microphone, what the electronic system is picking up is your sound wave signal, which is looking something like this. So all these are our observations. The amplitude of your sound waves can be treated as the observations in our hidden Markov model, which is represented by our X. And at every time step over here, we would have a certain segment of the sound wave which corresponds to a certain pronunciation or a certain spoken words that we can recognize. And now what we want to do here is that we want to model this using the hidden Markov model, where the latent random variable actually corresponds to the particular word in English that we are speaking. For example, Bayes' theorem, and in this case here, this can be broken into a few segments in the pronunciation over here. Now suppose that each one of the segment here is our actual pronunciation, it's the actual spoken word, and this would correspond to the unknown latent random variable, where we wish to infer from the observed sound wave, the observed amplitude of the observed signal of the sound we denote as x1. and the hidden random variable or the latent random variable would be the actual spoken word that we wish to infer, which is denoted as Z1 in this case. So it's obvious that when we speak, all our sentences or all our pronunciations are going to be continuous. So this means that whatever that I'm going to speak at the sentence at this particular instance of time is going to be dependent on the previous instance of time, or the previous time step over here, as denoted by the Markov chain in this case over here. So as a result, what we are going to do here is that given all the sound wave signal that we have observed over here, suppose x1, x2 and x3, we are going to infer the actual spoken word of Z1, Z2 and Z3 from the microphone. Another example here would be target tracking. Suppose that I have an enemy airplane that is flying across our airspace, intruding our airspace over here, and the commander-in-chief decided to send a ship, a warship, to launch a missile to take down this particular enemy plane over here. So in order for this warship, or for this missile to hit that particular enemy plane, we would have to first get a location of this particular enemy plane at every instance of time, since it's a moving target. So we can use radar, for example, to scan the surrounding for this particular moving target over here. And the signal that we pick up from the radar, it's our observation. So at every time step, suppose that this is t equals to 1, t equals to 2, t equals to 3, and t equals to 4, for example. And every time step, I'm going to observe a certain signal from my radar, which I call x1, x2, x3, and x4, corresponds to the 4 observations of these 4 time steps from the radar signal. But what I want to really know from this radar signal is the location of the enemy plane at every instance of time, and that is of course a latent random variable which is unknown to us, and we wish to infer from all these sets of observations here. So that could be represented as Z1, Z2, Z3 and Z4 respectively, which corresponds to the pose of the enemy target over here in these 4 time steps. But of course, the first time step, the location where the aeroplane is at this particular location, it's going to affect where it's going to be in the next time step, because it's unlikely that this particular aeroplane is going to violate its dynamic model and fly out of the area over here. So it's going to be within a certain vicinity, as well as it's going to follow the dynamic of the particular airplane over here. Hence we can say that the current pose of the airplane is going to be dependent on its previous location over here, and it's going to form this hidden Markov chain, which are going to learn how to do the inference today. Another example here would be in the case of a robotic SLAM, which stands for simultaneous localization and mapping. This is actually a classical problem in robotics for the last 30 years. It has kept many roboticists very occupied in the last 30 years to work on this particular problem. And here is the graphical model that denotes the SLAM, or simultaneous localization and mapping problem. As the name implies, we're going to simultaneously localize the robot, which means that we are going to find the pose of the robot at every instance of time. And then what we are going to do concurrently would also to build a map of the surrounding. Now suppose that this is the floor plan of the building that we are looking at. We are going to put a robot to explore this particular area, and at the same time we are going to do localization of the robot at every instance of time with respect to a canonical reference frame. Suppose that this is our first frame, first robot frame that we or the first robot pose. So we are going to denote this as FW, and at every instance of time we are going to find the robot pose with respect to this particular reference frame over here. So this would be denoted by x, k, k plus 1 and k minus 1 over here. And every instance of time when the robot explores the environment, besides the need to infer its current location with respect to the reference frame, concurrently we also want to map out the environment. Suppose that it's mounted with a laser sensor that allows it to detect obstacles in the environment. So as the robot explores the environment, we want to create something that looks like this, which is a occupancy grid map, where the white region represents empty space, the black regions represents occupied space, and it's every cell here, it's actually every grid cell over here, it actually contains a value from 0 to 1, where 0 means that it's unoccupied or free space, 1 means that it's occupied space. Anywhere in between is shown as a uncertain area, which is in gray over here. And this can be modeled as a graphical model that looks like this. So we'll see that the map structure, the location of these obstacles is going to affect our measurement, as well as the pose of the robot is going to affect the measurement. And U here is our control command. It's our control command. This means that at every instance of time, I'm going to give the robot at this particular location, I'm going to tell it to move forward or move to somewhere else in the next time step. So this is my control command, and obviously it's going to affect my current pose. So the end result of this is that we want to simultaneously localize the robot pose, which is x over here, shown as the latent random variable, as well as to build a map of the surrounding. So the map structures over here, M, they are all going to be the set of latent random variables. And what we have observed is the Z's that is from our sensors. It could be a laser sensor, as well as our control command that is given to us. So now, similar to the airplane example, the robot pose at this particular instance is not going to jump abruptly to another location, because we are not going to teleport this particular robot from one location to another. It's going to follow its motion model or the dynamic constraint of the internal mechanics of the robot, and hence we can say that the current pose is actually dependent on the previous pose, the previous location of the robot, as well as the control command. And the task over here would be to find all the latent random variables. We can see that over here it's also a hidden Markov model, where this particular guys over here, it forms a Markov chain, a linear Markov chain, and it gives rise to all the observed random variables over here. The last example that we are going to look at is the financial forecasting, where we can also model the prediction of future market behavior from historical data. So here, what's happening here is that we can actually treat every one of these observations here, all the observations of all the factors that gives rise to the latent random variable, which is the outputs of the Straits Times index, for example. So this is my latent random variable, which what I want to infer of the current financial market value, and this is going to be dependent on many of the observations that I can make. For example, the Prime Minister or the President has fell sick to this particular day, and this is going to affect the stock market, or the housing price went down or went up. It's also going to affect the financial market. So here we would have a set of observation here, and we also assume that the previous day financial market is dependent on the current day financial market. So and a set of observations, of course, and this eventually it forms a linear Markov chain or hidden Markov model, where we can make use of all the observations to predict the market outcome over here. And what's interesting here is that after we have predicted all the market value over here, xm plus 2, we can also try to predict. So all this, if we have observed all these values already, we can also try to predict what is going to come next in our market value over here. Now let us look at the individual terms of the joint probability distribution. We'll first start by looking at the transition probability, which we have seen to be in this particular form over here. It's actually a conditional probability distribution of Zn conditioned upon Zn minus 1, which helps us describe the dependency of the latent random variable, or the current latent random variable, on the previous latent random variable. So following the mixture model, this random variable of latent random variable of Zn, it's also going to be a 1 of k coding scheme. This means that Zn is going to take 1 out of k states over here. And this is to describe which component of the mixture is responsible for generating the current observation xn. So here, what it means is that xn over here is our observation. Suppose that this is our observation of xn over here. And what this means is that since if you recall the particular diagram that I have shown in the earlier slides of the clustering, each one of these observations is going to be assigned to one particular cluster. So what this means is that the 1 of k coding of Zn is going to tell us which cluster that xn, this particular observation of xn, is going to be assigned to. So suppose in this case, this is my cluster number 1, cluster number 2, cluster number 3. And if xn belongs to cluster number 1, then Zn is going to be equals to 1 over here. And what's interesting here is that, as I've mentioned many times throughout the lecture, that Zn, which is in the current state, current time step, it's going to be dependent on the state of the previous latent random variable of Zn minus 1. Now suppose that the previous observation is over here in cluster 3 over here. So this is xn minus 1, where Zn minus 1 is equals to 3 over here. So now what's happening here is that we are going to say that to make use of this particular conditional probability, or the transition probability, to tell us what is the probability of, given that the previous observation of xn minus 1, what is the probability that xn is going to take a class, is going to be assigned to cluster 1, or xn is going to be assigned to cluster 2, as well as xn is going to be assigned to itself. Suppose that k here is equals to 3. That means that we have 3 states over here. So it should become apparent here that the transition probability of Zn conditioned upon Zn minus 1 would be described by a k by k matrix, which we denote as A over here. What this means is that since each one of the latent random variable is going to take 1 out of k states over here, this means that there would be k possibility of Zn conditioned upon a particular choice of Zn minus 1. And since there are k possibilities of Zn conditioned upon a particular case of Zn minus 1, and there are also k number of possibilities for Zn minus 1. So we'll end up with a k by k table in this transition probability distributions. And where each element over here is known as our transition probabilities, which we'll denote as Aij. This means that this is going to be, Aij is going to be our ith entry in the row and the jth entry in the column, and this corresponds to Aij over here. So the entry of Ajk in our transition matrix, it's going to describe the probability that Znk is going to be 1. This means that I'm going to take Zn is going to take a state of k, conditioned upon Zn minus 1 is going to take a state of j over here. So this particular entry over here, it's going to tell us that this particular conditional probability, that given that the previous step Zn minus 1, I'm assigned to the jth cluster, or the jth state, that my current state is going to take k equals to 1 over here, is going to have a probability of Aj k. So the second property of the state transition matrix is that every entry of Ajk is going to be between 0 and 1. this would make every entry a valid probability value, with the sum of all the columns of on a particular row to be equals to 1. So what this means is that this is actually an obvious result of the first definition over here. Since we say that condition upon j equals to 1, this particular conditional probability distribution is going to tell us znk, what is the probability of znk equals to 1, or writing it in general, it will be the probability distribution of Zn condition upon Zn minus 1 taking a state of equals to j. So we are looking at a particular row of our A matrix over here, where this guy over here is going to be j. It's fixed at the particular value of j equals to or rather Zn minus 1 equals to j, taking a state of j, and we are going to look at all the possibility of Zn. So all this possibility of Zn, every one of this entry over here is going to be the probability of Zn taking that particular state, given that the previous state of Zn is equal to j over here, and all this probability over here, it must sum out to 1. And this can be obviously described by the second condition over here, where the sum of the whole row of j over here should be equals to 1, and every entry here should be from 0 to 1. We also call this particular matrix the stochastic matrix. So it's also obvious that since we say that the whole row or every row of the stochastic matrix or the state transition matrix over here must sum out to 1, what this means is that for each row we would need k minus 1 parameter to describe it, and since we have k rows over here, altogether we would have k multiplied by k minus 1 independent parameters to describe the state transition matrix. We can also visualize the state transition matrix or the transition probabilities using what we call the transition diagram as shown in this particular figure over here. So each one of this square over here, it represents z taking a certain state of k equals to 1, k equals to 2, or k equals to 3 over here. And since this is going to represent our state transition matrix, what it means is that suppose that Zn minus 1 is at a state of k equals to 1, or the state of 1 over here, we'll look at the transition probability from this particular state to Zn over here. So this would be described by the three transition probability of starting from that conditioning on Zn minus 1 equals to 1 over here. So what this means is that I'm looking at this particular probability of Zn condition upon Zn minus 1 equals to 1 over here, the state of 1 over here. So the probability this particular probability over here would consist of 3 entries, since there are 3 states to each Zn over here. And here the probability that the next state where Zn is going to take a state of k equals to 2 is given by this arrow over here, which is denoted by A12, as well as the next state taking the same state of k equals to 1 is given by this arrow over here, returning back to itself, where the probability is going to be A11, as well as the probability that the next state of Zn going to be k equals to 3 over here. It's given by this particular probability over here, which is described by A13, conditioned upon that Zn minus 1, which is the previous time step, is taking a state of 1. We can also see that this is true for any other Zn minus 1 state. Suppose that Zn minus 1 equals to 2, then we'll start from here, and the conditional probability here would be describing these 3 probability values. They all should add up to 1 over here. Notice that this particular state transition matrix, which is visualized as the transition diagram over here, actually just corresponds to that particular k by k matrix which we have seen earlier. And it's also important to note that this is not a graphical model, it's just a state transition probability which describe the probability distribution, or the probability table of this conditional probability distribution Zn and Z conditional upon Zn minus 1. So the state transition diagram in the previous slide show us the probability distribution of Zn conditional upon Zn minus 1. And if we unfold this particular transition diagram into a lattice or trellis representation, as shown in this figure here, we can see how the states and the probability value transits from one step or one time step to the other time step. So in this particular case here, this is t equals to 1, the time step 1, this is t equals to 2, t equals to 3, and t equals to 4, and so on and so forth. So what it means is that here t equals to 1 at the first time step, there could be z1, where is the first latent random variable. It could actually take one out of these three states over here. There is a certain prior probability of z1 taking a state of 1, z1 taking a state of 2, as well as z1 taking a state of 3, as well as the observation or the observed random variable, the probability of x conditioned upon z1 equals to 1, and this will be the probability of x conditioned upon z1 equals to 2, and so on and so forth, z1 equals to 3, as well as the state transition probability that is described by the edges over here. This represents Zn conditioned upon Zn minus 1. We can then write the conditional probability distribution explicitly into this particular form over here, where we say that the probability of the latent random variable at this current time step, Zn, conditioned upon the latent random variable in the previous time steps, denoted by Zn minus 1, and the state transition matrix of A over here, is given by this probability distribution in this equation here. We can see that what this means is that we are looking at every entry of the state transition matrix, where Zn and Zn minus 1 is going to take a particular state. Now suppose that we are going to, this is obviously a k by k table, a k by k distribution over here. This whole distribution is a k by k distribution, which we can write as Zn and Zn minus 1. Now suppose that Zn is going to take a state of k, and which means that I'm going to look at the kth entry of Zn, and as well as the jth entry of Zn minus 1. I'm going to look at this particular value over here, which corresponds to A of j and k here, which is given by this guy over here. So we can see obviously that when Zn minus 1 equals to j, taking a state of j, then this guy over here is going to be equals to 1. And if Zn is going to take a state of k, then this guy over here is also going to be a state of 1. And this probability value of P of Zn taking a state of k and condition upon Zn minus 1 taking a state of j is going to be equals to A, j, k over here. And since the initial latent random variable of Z1 does not have a parent node, it is represented as a categorical distribution. This is similar to the mixture model, which we have seen in the previous lecture. And we will say that the probability distribution of Z1 is conditioned upon pi, where pi over here is our categorical distribution parameters, which is written as this product term over here, the distribution, where each one of these pi term should sum up to be 1. So this is equivalent to, we are saying that Z1, P of Z1 is going to take a certain distribution in the categorical distribution. So in this particular case, we have k here equals to 5, where k is going to take a state of 1, 2, 3, 4, or 5 over here. And all this probability distribution over here, the values over here are going to sum up to 1. The next probability value that we are going to look at in our joint probability distribution would be the emission probability denoted by this conditional probability distribution over here, where xn is our observed random variable condition upon the latent random variable, and phi over here, which is all our unknown parameters that describe this particular emission probability or the likelihood function over here. So here phi is going to be a k set of parameters governing the distribution dependent on what's our current state going to be like. So in this particular case, if I look at the probability distribution of xn condition upon zn equals to 1, for example, then what I'm looking at would be I'm going to take xn condition upon zn equals to 1, this particular joint distribution over here, to be dependent on the first parameter, the first set of parameter over here, which I write as phi 1 over here. And in this case here, I will have k number of this particular distribution, which is dependent on this parameter. So it can be a Gaussian if xn is continuous, or it can also be a probability table if xn is discrete. So in the case where xn is continuous, what this means is that for every state that zn is going to take, I would have a different set of mu and sigma that governs this particular probability distribution over here. And in the case where xn is a discrete state, so for every zn taking a certain state, I would have a set of phi which denotes the probability distribution table that tells me what xn is going to take. So xn in this case could be since it's also discrete, what it means is that xn would be taking 0, 1, 2, or any states over here, and dependent on zn, suppose that zn equals to 1, condition upon zn equals to 1, so this particular probability distribution table is going to be given by phi 1 over here, and so on and so forth. So in the case of xn, condition upon zn equals to 2, then this distribution table over here is going to be given by phi 2, and all the way until 5k over here. And hence the emission probability can be formally written by this function over here, where we are going to take the product over k terms of this, since we have k sets of this random variable, depending on what state of zn is going to take. So as I have mentioned earlier, for each set of for each state that zn is going to take, we are going to take that corresponding phi in the set as our underlying probability distribution. Now suppose that zn over here is going to take the k states, then this guy here is going to be equals to 1, and the conditional probability or the probability distribution of xn is going to be given by this 5k, the parameter of 5k over here, and all the other terms over here are going to be 0. Or we can also think of it this way, that for a given value of phi, this particular probability distribution will consist of a vector of k numbers that corresponds to the k possible states of the binary vector zn. Now it's also important to note that the hidden Markov model is a homogeneous model, or otherwise known as a time invariant model, where all the underlying parameters that governs the hidden Markov model distribution stay constant regardless of the time step. This means that zn, for example, z of 10 condition upon z 9, it is going to have the same A matrix that governs this particular transition in comparison to the probability of z2 condition upon z1a over here. So all these A's, they must remain the same. This is also true for our emission probability of xn condition upon zn and phi over here. So regardless of what's the index of n over here, the phi, which is the underlying parameter for this conditional probability distribution must remain the same. And in other words, we call this the homogeneous model or a time invariant model. Now what's interesting here is that if the state transition matrix of A, where all the rows, the entries in the rows are all going to be the same, what this means is that the data are going to be independent of each other. All the latent random variables are going to be independent of each other. Now suppose that this is the row ith row over here. What this means is that Zn minus 1 is going to take a state of I, and what this means is that if all the entries over here are going to be the same, it means that there's an equal chance of from Zn minus 1 taking a state of I going into every other state. So this means that the next state of Zn is going to be independent of the state of Zn minus 1. And what this means is that the hidden Markov model that we have degenerates into just a mixture model, as what we have seen in the previous lecture. Now we can see that the joint probability distribution of our hidden Markov model over both the latent and observed random variables, it can now be formally written as this expression over here, where we have the joint probability distribution of x and z conditioned upon our parameters, or our unknown parameters, which we define as data, where data over here is going to be pi, which is our categorical distribution for the first latent random variable z1, as well as our state transition matrix A, and our emission probability of phi over here. And this can be written as the product of the prior probability and the transition probabilities, as well as the emission probabilities.